wanted to open by talking about something we all know, which is that climate is critical to wine grapes, and in many different ways, but I'm showing you one of those major ways here. So this map is showing the variation in the timing of maturity due solely to the different varieties that are planted in different regions of Europe. So we've sort of tried to wash away the climatic effect and ask, what's the difference in ripening times based only on what varieties different regions are planting? And to do that, we have to standardize the data. So in this case, we've standardized all the data to a reference variety, which is the early ripening Chasselas. So if you look at the figure and you see the light green dots, those are areas that tend to plant extremely early ripening varieties on average, like Chasselas. And if you look at the circles that are a darker or sort of a muted purple going to a darker and darker purple, those are areas that on average tend to plant varieties that are ripening 2 to 3 to 4 to even 5 weeks later than Chasselas. And of course, you see there are some strong latitudinal patterns. Areas in the north, not surprisingly, are tending to plant early ripening, fast ripening varieties. And areas in the south, in the southern tip of Italy, in Greece, are planting much later ripening varieties. There's some variation in that. If you look at the Loire Valley, you'll see it's a bit more purple than surrounding areas. That's in major part because the Loire Valley tends to plant Cabernet Franc, which is, of course, a later ripening variety. Woo, that's exciting. Hold on, everybody. Oh, I can see it, but you guys can't see it. I don't know what to do. Thanks. Okay, well, when it comes back, we'll get to see that we can look at these figures across the globe, and I'm about to show you the western coast of North America, the same figure, data taken from the same location, any second now. This is an exciting vintage report for technological issues. Okay, so here we have it. It's the same exact type of data. Again, the circles represent the variation in the timing of maturity due just to the varieties that are planted in different regions. And what you see are some similar patterns. Areas in the north and on the coast are tending to plant earlier ripening varieties on average. Areas a bit in the middle of the state and southern are tending to plant later ripening varieties. You don't see the same variation you see in Europe. That could be in part due to the climate variation in California, but is definitely due in part due to the fact that we just don't plant anything other than mid and early ripening varieties on average in California. So we don't tend to plant in any quantity those later ripening varieties. And so what I'm interested in and what I work on is what causes this variation. Obviously, there's tremendous variation in when different varieties ripen, and that's due simplistically because varieties have different developmental rates, they respond to climate differently, and of course they fundamentally have different phenologies, which is what I'll talk about today. So we tend to focus on the 4 major phenological stages during the growing season. I'll talk today about budburst, flowering, veraison, and a little bit about maturity. And I want to just walk you through how we try to actually model and predict these different stages year to year. And that's what we do in my lab. We try to understand how we can better predict the variation in maturity, or not maturity, in phenology due to different spaces, different geographies, different climates year to year, and also due to different varieties. So unfortunately, the one stage I won't be talking about today is maturity. That's because we just don't have great data on maturity in order to accurately model it. To accurately model maturity, we need sugar data repeated across the end of the growing season. So we need more Brix data than we have access to currently. That is, if you have lots of long-term fantastic sugar data repeated across the end of the growing season that you want to share to improve models, please let me know. And that goes for all of the phenological stages. So what I want to do now is just walk you through how we model each of these first 3 stages, budburst, flowering, and veraison. So we'll start with budburst. To think about budbursts, this is actually by far the hardest stage when we try to model it or understand it, and it's because it's preceded by a stage that we cannot observe effectively. So budburst is preceded by dormancy, and specifically by when plants exit dormancy. We need to estimate or guess when plants are ending their dormancy in order to have any hope of trying to predict when they will burst bud. And dormancy is one of the more complicated things to try to understand just from a basic physiological standpoint. So when we think about dormancy, it's this period in the winter that plants are trying to get into where they can be maximum hardy. So they can withstand the lowest temperatures during the whole season of their annual season of growth. And effectively what they're trying to do is accumulate enough chilling units or chilling hours or chilling days or whatever you want to call it some amount of cold temperatures that they feel that they've experienced that is saying to the plant, winter has passed, and the next temperatures you receive that are warm probably indicate spring. So plants are trying to enter this phase where they're nice and chilled and staying cold and staying dormant and aren't responding to sort of erratic warm temperatures. And we actually think in the scientific literature of multiple stages of dormancy. The first stage that most of us talk about when we talk about colloquial dormancy is endodormancy. So this is when plants are trying to accumulate enough chilling hours, and they will actually exit endodormancy and enter a phase called ecodormancy when they've accumulated enough chilling hours and can start responding to heat. So when I talk about exiting dormancy or trying to have a dormancy break date, I'm really speaking about this endodormancy phase and the end of it. And to model it, we used what's called a smooth Utah model, which has a couple of features I wanted to walk you through. So all these models are based predominantly on temperature, and I'll focus on temperature today. I'm going to walk you through, as an example, the temperature from last year's season. So I have data from the Napa Hospital Weather Station. Obviously will not be exact to your vineyard unless that's where you're growing, but gives us a sense of the patterns for the year, starting in September and going through March on the horizontal axis. And I'm just showing you the minimum temperature on the vertical axis. So the first thing to know about how plants accumulate chilling is that we don't expect that they can sense chilling below some minimum temperature. So plants effectively cannot be accumulating chilling below freezing, and more probably we expect that they don't accumulate any chilling below the low or high 30s to possibly even the low 40s. So those temperatures effectively mean nothing to plants unless they get so low that they're actually damaging. They're not accumulating chilling during that period. They need a special range of temperatures that are cool enough to accumulate chilling, but not too hot. So the other thing these models always include, or generally include, is the idea that extreme hot temperatures during the period when plants are accumulating chilling can negate or effectively subtract chilling units. So if a plant is trying to gain, say, 100 chilling hours, is something we commonly think of for wine grapes. Trying to gain 100 chilling hours, it has 80. If it experiences a very hot day or several days in the 60s or 70s, you might find that plant has effectively been reset to 60 or 70 chilling units. So it's going to actually need more cold to overcome those hot periods, and we include that in our model as well. So all this part of the model does is give us an estimate of when we think the plant has exited dormancy. And from that, we can try to build onto it and say, okay, when does the plant actually bud burst? And for that, we use a type of model which is called a Wang and Engel model. But effectively, all that means is the curves that we're fitting look like this. They have temperature on the horizontal axis, a rate of development from 0, meaning the plant isn't developing at all, to 1, meaning it's developing as fast as is physiologically possible at 1, and there's some optimum temperature which they develop as fast as they possibly can. What this effectively means is each growing degree day hour or such that you think of is not equivalent. Plants are actually developing faster unit Fahrenheit when those temperatures are closer to the optimum temperature than they are developing per unit Fahrenheit when those temperatures are lower. And these are models that fit much better than a simple growing degree day approach, and that's why we use them. They have an optimum temperature and then they drop off swiftly at the end. And so we try to fit this sort of heat accumulation model for bud bursts. We have the dormancy date. We now are asking how do plants accumulate heat, and we try to fit how much heat each plant actually needs. Those conditions definitely depend on the different varieties. And I should note that dormancy probably depends on different varieties as well as on the exact conditions each year may affect exactly how many chilling units you need to exit dormancy. So to fit these models, just to walk you through what we actually need to do and the data we need to have, we have to have phenological data across multiple sites and years. We need multiple years per sites, and the more sites and years we have, the better we're able to estimate these curves and estimate the models. We have to have matched local climate data. Obviously, the more local it is, the better for our model interpretation and fitting. And then we have to set some constraints on the model. We basically set these through experiments or through physiological knowledge that we have. So in all of the models I'll show today, we set 0 as the minimum temperature. Plants can't develop below 0. We set, or 32 degrees Fahrenheit, excuse me. And then we set 40 degrees Celsius or 104 degrees Fahrenheit as the maximum temperature. We assume beyond that plants are not developing at all, and there's some very different process going on, probably tissue damage. So we use this shape of model for bud burst. We use the same fundamental shape to model both flowering and veraison. We fit a different curve for each stage though, so optimum temperatures vary for bud burst, they're different for flowering, and they're different for veraison, and we adjust for that for each stage. So just fundamentally to walk you through how it goes, these models do build upon each other. You can't estimate any date without estimating the phenological date before. So we start with this dormancy model that I talked about that's all about letting plants accumulate a certain amount of cold, enough chilling for them to get through the winter season and to be exiting basic dormancy or exiting endodormancy effectively. Once we have what we think of as this dormancy break date, which I should say usually happens before the beginning of the new year, then we start modeling enough heat accumulation through this special curve to lead to bud burst. Once we have the bud burst date, we estimate how much heat accumulation is needed to get from bud burst to flowering. That gives us a flowering date. Once we have that, we estimate how much heat accumulation is needed with these specific curves to get between flowering and veraison, and that gives us a veraison date. We know that varieties vary in how they respond to temperature, and we try to model that. There's several major ways to do it. One is that we can just expect that they have different curves. So you might expect that different varieties have a different optimum temperature. The shape of the curve can vary slightly. You might also expect that different varieties have different maxima temperatures that they can experience and sustain. We don't have data on that yet, so it's a hard thing to model. But that's how we can have them vary. The other way they definitely vary is how much heat they need and how much chilling they need. So different varieties require a different amount of chilling to break dormancy, and they definitely require a different amount of these heating units to get to the different phenological stages. And that's why they mature up to 6 weeks differently in the end. So we have these models in my lab fit actually for 11 different varieties, and we're fundamentally interested in using it to understand phenological variation across space and time, and to project that variation forward and ask what we can expect for phenology over the next 40 or 80 years in the future with climate change. But we take those models and first we have to validate them and see how well they're working, and that's what I wanted to show you today, which is looking at these modeling results for these 3 critical stages for data coming from Napa. Oops. So this result is showing our estimates of the phenological event dates for bud burst in green, flowering in yellow, and veraison in red for Cabernet Sauvignon. And it's plotted against data that was shared from Napa growers across 1985 to 2005. And I'm showing you both what the model predicts and what we observed in that year. It's a bit hard to see, but if you start on the bottom with bud burst, you'll see there's a faint green line running through the years. And that's actually what we observed on average across Napa for the bud burst date in those years. And then the darker green line is what the model predicted. And what you see is the model does okay for bud burst, it does better for flowering, and it does quite well, I would argue, for veraison. It's quite hard to even see that faint observed line underneath the predicted line. It's not surprising that the models get better through time because they actually build upon each other. So the model has sort of a chance to improve at each event date. It gets bud burst a little off, but it can correct more in flowering and veraison. As I said, we do this for 11 different varieties. I'm just going to show you 3 of the major varieties for which we had enough data to compare in Napa. So the next one is Merlot. Again, same design. The faint line is what we observed that year. The darker line is the model prediction from these temperature-only models. And you can see it's quite hard to even see the difference once we get to veraison from Merlot. So they're quite accurate. We were surprised by how accurate they are for this region. I should note these models are built on completely French data, so we were really applying them outside of their ranges when we brought them into California, and they did quite well for most varieties, but certainly not for all. So this is Chardonnay. You can see Chardonnay actually does quite good at the beginning of the record. It's hard to see some of the observed data, and then it gets a bit off as we go to the last 10 years of the record. You can certainly see that fainter red line is quite off in some years compared to the prediction. It does consistently though, get an early year correct compared to a late year. It's just a question of how correct is it in terms of the absolute date. Is it getting the date exactly correct? We have run these models briefly for 2017 to see if there are any anomalies. The big thing we were expecting is some sort of impact of these really high temperatures. So I've highlighted in red the area where we tend to think that this is more of a negative developmental temperature for plants. We don't expect development to ever be increasing in its rate over these temperatures, somewhere around 84 to 85 degrees. Again, this is from the Napa County Hospital for last year, just running from March to the end of September. And I'll just show you on the bottom of the figure, you just saw the dates that we actually expected for veraison in our model. Again, these are average dates. We're averaging across large geographical scales in these models right now. So this is across all of Napa in our minds. You can see for Cabernet, Day 2014, which is the 8th of August, veraison day 211, which is the 3rd of August, and 2014 or 8th of August for a Chardonnay. These are not dramatically unexpected dates for us in terms of long-term observational data or in terms of other years where we have model predictions. We didn't see anything dramatically alarming in sort of the phenology that we saw from the model predictions for 2017. For these varieties, I should say that we had a couple other varieties that are not as commonly grown in Napa, and we did see what we would call a phenological delay for last year's data in those varieties, which I'll very quickly explain because I know I'm over. The critical thing to remember about all of these models is that they have a period where development increases per unit temperature. It's getting faster per unit of temperature. And then they have an optimum, and then they drop off a cliff in this red area. So we expect actually that the development between flowering to veraison would slow dramatically at these higher temperatures for a very brief period of time, after which you really expect tissue damage, tissue loss, abortion of flowers, or sort of a totally different process than even continuing on in development. And so that's the concern. In our projections, this did not work at all, but I'll just walk you through it. For certain regions, we see this happening for sure in the future. So this is a projection of 13 different varieties for a region in Europe, which will go unnamed. We project back in time to 1960, all the way up to 2100. That's what I'm showing on the horizontal axis. And again, that day of year is on the vertical axis. What you see in sort of the bottom varieties is that they're getting earlier by many, many weeks over time. That's what we expect on average. But what you actually see is that some of the varieties, those later ripening varieties, are beginning to delay. And we expect that's because they're seeing these high temperatures that actually slow development and aren't able to develop as quickly when they reach that temperature range. So just in conclusion, phenological models that we're working on are predicting fairly accurately Napa at a large scale. They suggest development delays at high temperatures. That's how we fundamentally model phenology. We haven't seen it this year in the data that we have, but certainly there's a potential for it in the future, and we see that across our projected models. Many people helped on this project, so thanks to them. And with that, and a little bit of a delay, my apologies, I'll take questions.
So, Elizabeth, there are two questions on Slido. I'm just going to convey them, and then we'll ask the room. How does pruning date affect bud break date?
We don't include that in our models. So it certainly has an impact, but it's not currently in our models, so I wouldn't want to comment on it from that perspective. My apologies.
Okay. Based on chilling units, can bud break be delayed by a warm winter?
Yes, that's one of the big things we expect. If you have a warm winter, you would start to see this issue where the chilling units are getting negated. And we don't have that in our models based on like a physiological dream. We have it because when we observe the data and try to fit the models, you see these warm winters delaying phenology much more than you would expect if plants are able to just accumulate chilling and ignore the warm winters. So those warm winters, depending on when the warmth hits, could delay effectively this dormancy break date that we can't see, which in turn would delay bud burst. In general, those warmness periods have to happen, in September to December for this region, we would expect.
On that same line, Elizabeth, are you saying vines won't undergo bud break if they don't accumulate enough chilling units during dormancy?
So I should say you can almost try to observe the end of dormancy if you want. You can take a plant and let it have a lot of extra shoots, and then you can clip it and bring it inside. If it leaves out completely with no sort of odd bud break, then your plant has exited dormancy or endodormancy officially. So what we expect if a plant has not received enough chilling hours is really dependent on how many chilling hours it got and the exact climate conditions with regards to temperature. You wouldn't necessarily see that the plant doesn't bud break, but you would see sort of abnormal bud break. Specifically, you wouldn't expect all the buds to break. The bud break wouldn't sort of look as good or as high quality. And that's actually how we measure dormancy break. If the plant's completely flush and all the buds leaf out, we say dormancy is broken at high temperature. If you put them in a warm temperature and they fully break out, dormancy is broken. If you put them in a high temperature and 20% of them leaf out, we would think that there's really a minimal amount of chilling that's been met and the plant is still effectively trapped in dormancy.
Is ambient temperature the driving force, or is it actually soil temperature?
Oh, that's a great question. Is it ambient temperature or soil temperature? There are great debates in the literature about this, and I don't think we have an answer. The issue is that in our experiments, it's really hard to manipulate soil temperature and hold air temperature at a different temperature to tease that apart. Physiologically, we think it has to be due to soil temperature, but buds are fairly independent when you play around with them in a lab, so it's really hard to tell.
Maybe if there is one question in the room, we have time, and then we have to. Yes?
Have you normalized temperature data and looked at the effect of photoperiod on some of the other phenological attributes?
We haven't done it in our models because there's been a lot of work in the past done on photoperiod. So photoperiod we think is, photoperiod matters to most plants. It's critical depending on the specific stage and the specific plant. Grapes are a bit more photoperiod loosey-goosey than many other plants. When it appears to be most critical is getting the buds into dormancy in the fall, and even then there's a bit more play than we usually expect for perennial plants. So we've found, or historically people like Inaki Garcia de Cortazar have found, it doesn't have a major influence, so we don't include it in our models currently.
Thank you.
Thank you, guys.
Informative.